My name is Ralph Werbs, and I'm a professor in the Civil Engineering Department at Texas A&M University. And as we continue our review for the Fundamentals of Engineering exam, our subject for the next 3-hour session will be fluid mechanics. And we'll begin with a discussion of fluid properties and then go from there into fluid statics and dynamics. And of course, statics deals with fluid that's not in motion, and dynamics deals with flowing liquids and gases. And from there we'll take a brief look at fluid measurements as well. That will be a continuation, extension of some of the fundamental concepts that we cover in statics and dynamics. And as you know already, I'm sure that the key to mastering the fluid mechanics portion of the exam, like the other topics, is to work problems and lots more problems. And we're using the EIT review manual by Michael Lindbergh. And as you work in that manual and work through the problems and the samples and problems provided in the manual, you'll be on topic 7, which is fluid mechanics, chapters 22, 23, 24, and 25. Now, matter can be either solid or fluid, and the spacing of the molecules and the attractive forces between the molecules will govern whether or not we have a solid or a fluid. With a solid, the attraction between the molecules is such that there's a rigidity, and I can rub my hand across this tabletop and the table will not deform. But with a fluid, the spacing of the molecules is such that the attractive forces will allow any type of shear stress at all will be a continuous flow of the material. And so, as a definition, a fluid is a substance that deforms continuously under the action of an applied shear stress. And fluids can either be liquids or gases, and a liquid we can actually keep in a container with a free surface because the attractive forces are such between the molecules that we can contain a liquid in a container with a free surface. A gas just expands indefinitely, so we have to completely have it contained. And as we talk about fluid mechanics, we'll start with a discussion of fluid properties and go down the list here and define density and specific volume, specific weight, specific gravity, pressure, stress, viscosity, surface tension, and capillarity. And as we start with density and specific weight, before we, in just a few seconds, we'll define density as mass per volume, specific weight as weight per volume. But leading up to that, we need to talk about units just a bit, units of mass and force, and system international units. That version of the metric system is the direction we're all going. And my understanding is that the Fundamentals of Engineering exam is transitioning in that direction, and is primarily SI units, though both English and SI units are we're not totally to SI yet. We're still using some of the other units as well. And so in the SI system, mass is a kilogram and force is a Newton. And the British gravitational system, we're looking at slugs for mass and pound for force. And the English engineering system that many of us would certainly like to get away from, pound mass and pound force. And I think we are moving away from those units. They're a bit confusing. Now, Newton's second law is a good tool to keep the relationship between mass and weight straight. And force is mass times acceleration, so we're talking about gravitational forces. The weight is a mass times acceleration of gravity, and of course the standard acceleration of gravity is 9.807 meters per second squared, or 32.174 feet per second squared. So in the SI system, if we look at a weight is mass times acceleration of gravity, and the weight is in units of newtons, And mass is kilograms, and acceleration of gravity is in meters per second squared. So Newton is, by definition, 1 kilogram times meter divided by second squared. And the British gravitational system, if we rearrange the equation a bit and say mass is weight divided by the acceleration constant, a slug is a pound second squared per foot. And then in the English engineering system, we use a conversion constant, 32.174, to convert between pounds mass and pounds force. And we'll be working with density and specific weight throughout the evening, and you'll be working with those on the exam. And so density is mass per unit volume, and the units indicated here. Unit weight is a weight per unit volume, and the units indicated here, newtons per cubic meter, or pounds per cubic meter, or pound force per cubic meter. And again, in either the metric or British gravitational system, the specific weight is just the density times an acceleration constant. And the English engineering system is a little more complicated because you have to use that standard G sub C as a conversion. Now, for gases in particular, now gases are very compressible, and so density and specific weight is a function of pressure as well as temperature. Liquids in many engineering applications we treat as being incompressible, meaning that the density is constant with pressure. Then the density and the specific weight are still a function of temperature. And for typical type applications, if we use 10 degrees centigrade or 50 degrees Fahrenheit, the density of water would be 1,000 kilograms per cubic meter, or 1.94 slugs per cubic feet, or 62.4 pounds mass per cubic feet. And specific weight are the numbers indicated here. Now, specific gravity of a fluid is just the ratio of the density of that fluid to the density of water at some specified temperature and pressure. And since densities and specific weights are related by a constant, the gravitational acceleration constant, you could also define specific gravity as just the specific weight of the fluid divided by the specific weight of water. Moving into pressure, as we introduce the different properties and terms we'll be working with this evening, we can measure pressure from whatever reference we'd like, and the two typical reference datum is either absolute pressure, using absolute zero as the zero or the datum, or in many engineering applications, a majority in fact, we use atmospheric pressure as our reference datum, and we call that gauge pressure. Now, the absolute pressure is the gauge pressure plus atmospheric pressure, and we can use this diagram to visualize that. And so let's say we've got some pressure. So we've got pressures here in newtons per square meter, and this pressure A is above the local atmospheric pressure. And so in certain applications, if we wanted to work in terms of absolute pressure, the datum would be a complete vacuum, absolute zero pressure. But in many other applications, it's convenient to use the local atmospheric pressure as the datum. And so the gauge pressure is just the pressure over and above the atmospheric pressure. And so the absolute pressure, you'd have to add both the gauge pressure to the local atmospheric pressure to get the total absolute pressure. And of course, you could have a pressure B here, and B is a pressure in newtons per square meter that's less than the atmospheric pressure, and so you've got a negative gauge pressure, which is typically called a vacuum. Now we'll deal with stresses, forces per unit area, and typically you think in terms of normal stress and shear stress. When we're into fluid statics in just a second, though, in statics, the stresses are just normal because there can't be shear stress, or the fluid would be moving by definition, and it would be dynamics. Another property is viscosity, and viscosity is a measure of the resistance to flow when acted upon by an external force such as a pressure gradient or gravity forces. Now, Newton's law of viscosity gives us a definition of the absolute or dynamic viscosity, and this holds true for laminar flow. You'll have to remember laminar flow is where you have one layer of fluid flowing smoothly over the other layers, as opposed to turbulence, where there's a random turbulence of the fluid particles. And in random flow, and often this is pictured in textbooks as a plate which is held steady, and then another plate with some fluid between the two plates, and the second plate is moving over the first plate. And so the fluid particles move with the moving plate as the fluid deforms, and there's a velocity gradient, the change in velocity with distance from the fixed plate. And so the shear stress is proportional to the velocity gradient. And that constant of proportionality, the mu, is what we call the absolute or the dynamic viscosity. And so, of course, that's one way of a formal definition, but you can visualize how some fluids, molasses or syrup, has a resistance to flow. Your ketchup, you're pouring ketchup on your French fries, and it doesn't flow quite as freely as water would. And so this is a property that captures that tendency for some fluids to resist flow more than others. In different formulas, you often see both viscosity and density. And so we use the term kinematic viscosity, and to combine the two, kinematic viscosity is just the absolute viscosity divided by the density. And it would have units meters squared per second in the metric system, SI version of the metric system, or feet squared per second in English system. And of course, dynamic viscosity would be Newton seconds per square meter, or pound second per square foot. And again, there are tables that provide viscosities as a function of temperature, and some typical viscosities are given here for some typical temperatures. And you always remember that viscosities are very small numbers, because it's easy to leave the minus signs out. They're 10 raised to the negative 3 or negative 4 or negative 5 or negative something power. Small numbers rather than large numbers. Okay. Now, there's a phenomena that occurs which we call surface tension at the interface between a gas and a liquid. Intermolecular cohesive forces are such that there's an imaginary film formed, and you can do things like with a liquid at the surface. You can float a pen, or maybe an insect can float. Some object that has a density greater than the liquid can actually float in the liquid due to surface tension. And a related phenomena is capillary action, and that's caused by the surface tension between a liquid and a solid surface. And you usually picture that as a thin bore tube. Water will rise up in the tube as the liquid adheres to the sides of the tube. Or in the earth, in geologic groundwater aquifer formations, where you've got sand and gravel and a water table, the water will rise up in the little porous media between the pores, between the sand and soil particles, due to capillary action. So these are some of the basic properties of fluids, and we'll be using those as we continue on and cover the two broad topics of fluid statics and fluid dynamics, beginning first with fluid statics. And we can start there with talking about a hydrostatic pressure distribution. And the hydrostatic pressure is the pressure that a fluid exerts on a container. And if you've got a container of a liquid, it exerts pressure on the walls of the container. An object, you may have an object emerge in the fluid. And so the pressure increases with depth. At the surface of a liquid, there's zero pressure, but as you get deeper and deeper, the pressure increases, as indicated by this little diagram or schematic representing a pressure distribution, a linear increase with pressure with depth. And this is the basic concept and the basic equation that fluid statics is built upon. If we understand this equation, we can pretty well understand fluid statics. And so if you pick a couple points, some vertical distance apart, here we're using a liquid in a container, that's the pressure difference. We let P1 be the pressure here and P2 the pressure there. That the difference in pressure is just the vertical difference in elevation of this column or height of fluid times the specific weight, the unit weight of the fluid. And so if we let the Z1 and Z2 just be the elevations, and so the difference in elevation being H, which we call a head, then the pressure is just the unit weight of the fluid times the head between the 2 points. And we may also want to deal with forces, and a force is just a pressure times an area. And so those are the basic expressions that we work with in fluid statics. Let's see, what's the pressure 10 feet below the surface of a swimming pool? Just a typical problem looking at the pressure equation. And so if you happen to be at the bottom of a swimming pool and there's 10 feet of water on you, there's a vertical column of 10 feet of that fluid, and that particular fluid has a unit weight of 62.4 pounds per cubic feet, and there's the vertical column, the H, the head, is 10 feet, and so you've got a pressure on you of 624 pounds per square foot of your person. As another example, same thing, except we've got one fluid on top of another. And in this case, we've got gasoline floating on top of water. And so the tank has a 3-meter tall column of gasoline, and we want to compute the pressure at the bottom of the tank. So 2 meters of water, 3 meters of gasoline on top of that. We're interested right here on the bottom, what's the pressure? And so this point on the bottom is supporting a column of 2 meters at 9.81 kilonewtons per cubic meter unit weight, and then a column on top of that of the specific gravity is given as 0.73, so we multiply the specific gravity times the unit weight to get the unit weight of the liquid on top there. And so we can plug in the numbers and do that. And it's convenient to work in gauge pressure. We do that quite often, so most often as a matter of fact. So we'll talk about gauge pressure because if you, at the beginning. And so the unit weight of the water times the head of water, 2 meters of head, plus the unit weight of the other liquid, the gasoline, which is a specific gravity times the unit weight of water, times the head there, 3 meters, give you 41.1 kilonewtons per meter squared. And of course, if we go back to the diagram, the column of fluids above this point, we really left out one fluid because sitting above the surface of the gasoline, there's the atmosphere. So there's another fluid up there, the air. And so if we talk in terms of absolute pressure rather than gauge pressure, we'd want to add that column as well, and that's represented by atmospheric pressure. And so if we add the column of air, we'll add in the atmospheric pressure to the gauge pressure we just computed to get 142 kilopascals, and that's absolute. Another problem applying the same concept is a manometer. And manometer is a measuring device. It's a mechanism, one of various mechanisms for measuring the pressure in a container and a pipe. And we have to apply the principles of fluid statics to be able to convert a manometer reading to an actual pressure measurement in the container. And so in this particular problem, we have a pipe, some container, let's say it's a pipe of water flowing in the pipe, and we've got hooked up to a manometer, and this is just a tube, just a glass tube, And of course, I guess to simplify the computations, we could just run a piece of metric tube and just run it straight up and see how high the water rises in the tube, and that would do it too. It'd be a little inconvenient because the water might rise quite a few feet, and a manometer gives us a mechanism to make the measuring device fit into a reasonable space here. And so mercury doesn't rise nearly as much as water, since it's got a much denser, a greater density. And so typically, in many cases, we'll use mercury in a manometer. And so what we read is we can read where the meniscus of the mercury is here and here, and there's a 2 feet difference. And from that 2 feet difference, from that we can compute the pressure in the pipe. And so this provides us a good example of applying the same equation that we've been applying in the last few minutes. And so with any of the manometer problems, and there's all kinds of configurations of manometer problems and related type problems you could see on the exam. And so you want to just start on one end and work your way to the other end. And so let's start here in the pipe. And so we've got some pressure here in the center of the pipe. And that's what we want to compute. So we'll just write that as the pressure in the pipe. Now remember that in any horizontal plane, the pressure is always the same. So the pressure right here in the center of the pipe is exactly the same as the pressure anyplace else in this water system that's in a horizontal plane. So it's the same pressure there. And so we go to there, same pressure. Now we drop down to here, and we're going to pick up additional pressure because we're now supporting an additional column of water. 1.5 feet of water at whatever the unit weight of water is take us to here. And so we'll write that as just whatever the liquid is. It happens to be water, and the unit weight times the head. Now, whatever the pressure here is there, if we go across horizontally to right there, the pressure is identically the same there. So we know the pressure there is still that's the pressure there, except now we go up to here. And if we rise, we're taking some pressure off because we've got this 2-foot column of mercury, and so we need to subtract that off. And so whatever the liquid might have been, it happens to be mercury. Its unit weight times the vertical column of the liquid there, and we can write that there, and that gives us the pressure there. And we're going to use gauge pressure, so that's atmospheric pressure, so it's 0. So we write it as 0. And so we've just written an equation all the way through the system here, and we can start in any point and go to any other point and write such an equation regardless of the configuration. And the only actual unknown is the pressure in the pipe, because we know the 0 at one end, and then we know all of the different vertical heads for the different liquids that can be involved in the problem. And so we just plug in the unit weights and the vertical differences in elevation and run the numbers out, and we get that the pressure in the pipe is 1,604 pounds per square foot. Okay, we'll stay with the same equation and go in a little different application, and that's dealing with forces. Forces on objects that are immersed in the liquid, or maybe forces on the walls of the container. And there's different ways of computing forces and the locations of the forces. Now we have a plane surface. We can use these equations, and this is really the same equation we've been working with. A force is a pressure times an area, and the pressure equation is just a unit weight times a head. So we see this pressure term times the area to give us a force, and it's the unit weight of the fluid we're dealing with. And this time the head is going to be from the surface down to the centroid of the area upon which the force is being exerted. And this is geometry. This is going to provide the geometry to locate the force for us. And we've got a figure coming up in just a moment which will show us that this is a distance from the water surface to the center of pressure measured along the incline. This plane flat surface is inclined, and then this will be the distance from the water surface, or whatever the liquid is, the surface of the liquid to the center of the area. And then this will be the moment of inertia, and then the same distance measurement again in the area of the flat plane surface. And this will give us a location, and that's going to work fine for us when we apply this to a plain flat surface. Now, another approach which works for either a plane surface or a curved surface is we can think in terms of a vertical force and a horizontal force. And the horizontal force is really just if you take a vertical projection, and it has some area A, and then it has this pressure. And again, the pressure is just the unit weight times the head, which is measured from the water surface or the liquid surface to the centroid of the area. And then the vertical force is just looking at a horizontal projection, and then it's just the weight of the fluid on the horizontal projection. And so the weight is just going to be a volume of the fluid times the unit weight of that volume. And so this is nice, and it'll work for any shape. And then we'll also want to look at buoyant forces. There's applications of those as well. And so we'll run through 3 examples illustrating each of these approaches for dealing with forces in fluid statics. So the first of the 3 examples is an opportunity to apply the first technique. And so we've got just an object. Here's a triangular in shape, a plate. It's flat. It's on an incline. And so from 2 views you can see this triangular object happens to be in water. And we want to compute the force of the water on this object and the location of the resultant force. And so in different terms, the measurements, this is on a 45-degree angle. So we just measured from the water surface along the 45-degree angle the distance from the water surface to the center of the area, and the center of gravity is 1/3 of the distance from the top of the plate. And then we can measure to the center of pressure, and that's going to be 1/3 of the distance from the bottom to get that measurement. And we've got the measurements of the plate. It's 2 feet one direction, and vertically along the incline it's 2 meters, and then 1.5 meters. And in your Fundamentals of Engineering reference handbook, it gives formulas. There's a table that gives formulas for moments of inertia, so we can get the formula for triangular shape, and using that information go through the computations. And so let's do the computation. Now, basic equation. Force is pressure times A, and pressure is the unit weight times the head measured from the surface. That's a vertical measurement from the water surface to the center of area of the plate upon which the force is being exerted by the water. And then we need to locate the force, and we'll use this equation to locate it. We need the area, and so the area of a triangle is just 1/2 the base times the height, and we're given the base and the height, and so we can compute the area of the triangle. And we're not really given the area from the water surface down to the centroid, but we can compute that. And the way we'll do that, we are given the measurement from the water surface down to the bottom here. So we know that's 2.75 meters, and then we can subtract off, we can compute the difference in IC or LC and LP, and get the vertical component of that and subtract it off. Okay, so measured from the water surface to the bottom, 2.75 meters, and then subtracting off to get to the center of gravity. Well, actually, the center of gravity is just, we know the 1.5 meter length of the triangle along the incline, and the center of gravity is 2/3 of the way up, and so it's at a 45-degree angle. We multiply by sine 45 degrees and get 2.03 meters. So what we just did, we took that distance, and we got this distance as just being 1.5 times the sine of 45 degrees, subtracted that off, and it gave us h sub c of 2.043 meters. Now the L sub c, if you measure along the incline, that's just this number divided by the sine of 45 degrees. And so you take the h sub c divided by the sine of 45 degrees, you get 2.889 meters measured along the incline. Okay, the moment of inertia from the equation from the table in the reference handbook, we can plug in the base and then the 2 dimensions of the triangle, and so it's the base times the height cubed divided by 36, and that'll give us 0.1875 meters to the fourth. And now we've got the terms that we need to plug in to compute the force. We plug in the unit weight of the water, the 9.8 kilonewtons per cubic meter. We plug in the head, which is measured vertically from the water surface to the center of gravity of the flat triangular plate, and then we plug in the area of the triangular plate, and we get the force. And then we can use this formula that we've seen before to plug in the numbers to locate the force. And so we've got the distance along the incline from the water surface to the center of gravity, which we computed previously. We've got the area, which we've computed previously. And then we've got the moment of inertia, which we've computed here, which we can plug in. So we've got all the numbers to get that little incremental distance that along the incline, the incremental distance from the center of pressure to the center of gravity, and we can add that to the distance that we've already computed to the center of gravity to get the distance, the length from the water surface along the incline to the center of pressure. Okay, and so that gives us the force and the location of the force and the force, using the first set of formulas. Now, a second approach, and we could actually apply this second approach to the problem we just computed, but instead of doing that, we'll apply it to a different situation, just to have a different example. But it's more general in that it applies to any shape, curved as well as plain flat type surfaces. And so we're going to compute a horizontal component and a vertical component. And here's a problem to allow us to do that. We want to compute the force on the curved corner for unit width. So we've got a container, and again, it's full of water, and the water exerts a force in the corner down here, and we want to estimate the force. And so we can think in terms of horizontal and vertical components of the force, and so the horizontal component of the force is just going to be acting upon a vertical projection here. And so we're looking at the numbers. The force is the pressure times the area, and the pressure is the unit weight of the fluid again times the distance from the water surface vertically to the centroid of that area, or the projection, the vertical projection of the area. And we know the unit weight of the water, and we can look at the geometry, and the numbers are given from the water surface to the top is 10 feet, and we want to go to the center of the area, and we're actually working this problem for a unit width coming out of the paper here. So we've got a unit-wide rectangular area with a centroid 1.5 meters in the middle there. So 1.5 meters, 10 meters gives us 11.5. The area is 1 meter coming out of the paper times the 3 vertical meters. And so we got those numbers, and we can get the horizontal component of 338 kilonewtons. The other component is a vertical component, and so we project out horizontally and look at the volume. And so the volume above this corner is all the water above it. Take the volume, multiply that volume times the unit weight of the water to get the vertical force. And so if we jump back here, we've got that volume, and then we've got this volume. So we get the two volumes and add them together. And so again, we've got 1 meter coming out of the paper, and so we got 3 meters times 1 meter times 10 meters, and then we've got this area of a circle is what, 1/4 the radius squared times pi, and so we can get this area and then multiply it by 1 meter coming out of the paper. We're really into geometry here. This is more geometry than fluids, but so the volume of the top area is the 10 feet depth, the 10 meter depth, 3 meter width, and then a meter coming out of the paper, and then the circular portion of it, 1/4. The radius squared times pi, except we're looking at 1/4 of a circle, so 1/4 of that circular area times the meter thickness coming out of the paper, and that gives us a volume. And so the vertical force is just multiplying that volume, the 37.07 cubic meters, times the unit weight of the water to get us a vertical component of the force. So we've got a horizontal component of the force, a vertical component of the force, and we can combine the two just by saying that the resultant force is the horizontal squared plus the vertical squared. Take the square root of that, and so the resultant force is 496 kilonewtons. Okay, so that illustrates another approach of determining resultant forces on objects. Now, as we continue to work with forces, we can look at the special case of buoyancy and flotation. So the basic principles here: a body immersed in a fluid is buoyed up by a force equal to the weight of the fluid displaced, and a floating body displaces its own weight of the liquid in which it floats. And to give us a chance to think about that just a bit, we can go through this problem. And we want to compute the force in the rope. And so, again, we're working with water. We have a block of wood. And so here's the block of wood. It has a lesser density than water, so it floats, except it's not floating because there's a rope that's keeping it from getting to the surface. And so the buoyant force of the water is acting to make the block go upward, and the force is acting to hold it in place. And so we want to compute the force in the rope. And so the buoyant force is just the unit weight again of the fluid times the volume displaced. And so we look at the volume of the block. It's a foot in one direction, it's a foot coming out of the paper, it's 2 feet in the vertical direction, so the volume is 1 times 1 times 2. And so we've got a 2 cubic feet of wood there, so it's displacing the same volume of water, and the water that's getting displaced has a unit weight of 62.4 pounds per cubic foot. And so we combine the two numbers, and we get the buoyant force of 124.8 pounds. And so that illustrates the principle of buoyancy. And then to go ahead and solve the problem, we can do a force balance of all the forces, because we also have the weight of the wood. And so the wood has a volume of 2 cubic feet. It has a unit weight of 40 pounds per cubic feet, so there's gravity's acting on the wood to the tune of 80 pounds. And then the other force is the rope, and we don't know that. We're trying to compute the force in the rope, but if we sum up all the forces vertically, and so we've got a buoyant force that's lifting the wood block. We've got the gravity that's bringing it down, the weight of the block, and then we also have the force in the rope, so we got the minus signs there. And so we plug in the two forces we know, and that gives us the force we set out to find at the very beginning, which is the force in the rope of 44.8 pounds. Now, we could do that a different way, and just to give us a chance to think about buoyancy just a bit more. Now, the buoyant force on a submerged body is the difference between the vertical component of the pressure force on the underside and the upper side. And you go back to the block here. The block is supporting water. There's pressure due to the column of water above it, but at the same time, it's displacing water that's causing a buoyant force. And so now there's the buoyant force, and we can write that these are the basic equations. The force is just a volume times the unit weight, or the force is a pressure times an area. And if you notice, the equations are almost the same, because if you got a pressure times an area, you've got this vertical distance from the water surface to the centroid, and then you got an area, and so that's equivalent to a volume, and then both times multiplied by the unit weight. And so to compute the buoyant force, we can, acting on the underside is 5 feet deep. There's 5 feet of head. We got an area of 1 square feet. We've got a unit weight of 62.4 pounds per cubic feet. And then on the top, and the top has a head of, the top of the wooden block has a head above it of 3 feet of water, and it has an area of 1 square foot across the top upon which that water is setting, acting, and then it's got the same unit weight. And so by sort of visualizing the problem a bit differently, we get the same numerical answer of 124.8 pounds. Okay, so that's the laws of buoyancy and flotation, and that'll wrap us up as far as statics. And so now the water is going to start moving. We'll start dealing with flowing water, and with flowing water we call it fluid dynamics. And so as we move into fluid dynamics, most fluid dynamics is based upon the conservation laws. Conservation of mass, energy and momentum. And then extensions to, applications to, and different ways of manipulating and applying those basic 3 conservation laws. And then we add some things. Flow equations have to be somewhat empirical, in which we have to have empirical coefficients for it that we add to the conservation laws. And then we apply the basic concepts and applications, which could be categorized as flow and pressure conduits. And that means that we're dealing with pressures other than atmospheric pressure, or flow in open channels. And open channels means that there's a surface, if you've got a liquid, with a surface at atmospheric pressure. And we'll focus primarily on flow and pressure conduits. And there's one equation given in the reference manual, which we'll want to be sure to get to eventually, a little later as we go, that deals with open channels. So, just looking at the 3 conservation laws, mass, momentum, and energy. Let's begin with mass. And so, the basic conservation of mass, and we're just saying that if we have a control volume, and we've got flows coming in and leaving at two sections, the mass flux, the mass per time at one section is equal to the mass per time at another section. And so we can write the mass flow rate as volume times a density. And the volume we can write as a cross-sectional area of flow times a mean velocity flowing through that cross-sectional area. And so that's a representation of volume, and then we multiply that volume, or volumetric flow rate, of volume per time, times mass per volume, and that gives us a mass per time. And so whatever mass is coming into the control volume, the same mass is leaving, assuming no change in storage, a steady flow situation with no change in storage. And for incompressible fluids, and in most applications, of course, gases are very compressible. The densities change with pressure. But for most engineering applications of liquids, we assume incompressible fluids. The densities are constant with pressure. And so the rho 1 and rho 2 being the same, we can divide those out, and we can write the equation as the cross-sectional area of flow times mean velocity through that cross-sectional area coming into the control volume is equal to the same thing going out. Of course, this is a volumetric flow rate coming in and a volumetric flow rate going out. And another equation that we often associate with conservation of mass is the continuity equation, is discharge is volume times area. And so relating the two terms there. Okay. And just another example to give us the opportunity to think through conservation of mass and terms and units and equations related there too. We've got 3 kilonewtons per second of water flowing through this pipeline reducer. We want to determine the flow rate and the velocity in this section that has a diameter of 300 millimeters, and also in this section that has a diameter of 200 millimeters. And we know right off that the discharge is going to be the same. Whatever is flowing through this pipe, a volumetric flow rate through this pipe is going to be the same as a volumetric flow rate through this pipe. But the velocities are changing. As you change the areas, you change the velocities. And so we're really not given a volumetric flow rate, though. We're given a weight per time. And so we'll take what we're given and do the computations we need to do to arrive at the information that's requested in the problem. And so we need to know the unit weight of the water, or it could be any liquid with any unit weight. Let's say it's 9.8 kilonewtons per cubic meter for water. And we recognize that conservation of mass can be related to conservation of weight, in the sense that the specific weight is just the density times acceleration of gravity. A weight is just a mass times acceleration. And so we like to write the conservation of mass as a mass flux is just the density times a volume, and the volume is an area times a mean velocity through the area. At one location in one pipe is the same as in the other pipe, pipe 1 and pipe 2, or the different diameter pipes. But really that's the same thing as writing that the weight flux is just the unit weight times the volume times the unit weight times the volume at the two sections, and we can write it that way because we're actually given in this problem, we could have been given the mass flow rate, but we were given the weight flow rate of 3 kilonewtons per second. And so to get the discharge, if we divide the 3 kilonewtons per second times the unit weight of the water into the 9.8 kilonewtons per cubic meter, that'll give us a volumetric flow rate. We'll convert the weight flow rate to a volumetric flow rate. Another problem on the exam, you may be given the mass flow rate, and you've essentially got the same type of situation, which you can work just as easily. Velocity, the mean velocity of flow through this area A is just the Q divided by the A. And the area of a circle for a pipe is 1/4 pi times the diameter squared to get the A term here. And so we take the volumetric flow rate, the discharge rate, and divide it by the area, which we'll compute simply by substituting in a diameter of the pipe. And so in one case, the diameter of the pipe is 0.3 meters, and in the other case, the diameter of the pipe is 0.2 meters. And so we can substitute those in, and we'll get for the 0.3 meter pipe, we've got a velocity of 4.33 meters per second. And for the other pipe, the smaller diameter pipe, we've got an increase in velocity up to 9.74 meters per second. And so those two numbers combined to our previously computed discharge answers the problem. In addition to conservation of mass, we have conservation of momentum. And there are a number of different forms of the conservation of momentum equation. And some get fairly complex, and on the fundamentals of engineering exam, we would anticipate the impulse momentum equation form of conservation of momentum. And this is just saying that if you take a control volume and sum up all the forces acting on that control volume, it's just the change in momentum, and that's expressed as a density times a volumetric flow rate times vector of the velocity out minus velocity in. And since force and velocities have directions as well as magnitudes, they're vectors, we can write this equation in the 3 dimensions of the coordinate system. Right? The sum of the forces in the x direction is the density times the flow rate times the velocity out, which we can write as velocity 2 minus velocity 1, the velocity into the control volume, in the x direction, in the y direction, and in the z direction. And we solve a problem here in the z direction. Here we've got a pipe. It makes a 90-degree bend, and change in momentum as it goes around the bend here, and that means that the water exerts the force on the pipe, and the pipe vice versa exerts a force in the opposite direction on the water. And so the water is flowing at a given flow rate. The pipe has a given diameter, and we want to compute the reaction on the water and the z direction in the bend. And so the water is exerting a force, and the force of the pipe on the water is going to be the same force in the opposite direction. And that gives us some numbers to plug into our impulse momentum equation. We need to know the density for the fluid, and we're working with water, so we know these numbers. And the density of the water is 1,000 kilograms per cubic meter. And we'll need to plug in a velocity. And so velocity is discharge divided by area, and area is, again, for a circular pipe, is 1/4 pi d squared. And so we can plug in the flow rate, divide it by the area, and so plug in the diameter, 0.15 meters, to get an area. A discharge rate divided by cross-sectional area of flow will give us a velocity of 50 meters per second. Now, we needed the velocity to be able to plug in, and really there's a 90-degree bend, so in the z direction we've got a velocity coming this way in the z direction, but going into the bend there is no component in the z direction, so of course there's a velocity in the x direction, but in the z dimension there's zero velocity going in, and whatever the velocity is in the pipe coming out will be in the z direction. And so we've got 0, and again we all realize there's an absolute velocity of 50 meters per second, but when we divide it into the vectors of directions, and in the z direction there's 0 velocity, and then coming out of that bend, that control volume, is 50 meters per second. And we know the volumetric flow rate it was given, so we plug in the Q, and because it's water, and we've got constants in our tables that tell us the density of water, we can plug in the 1,000 kilograms per cubic meter, and then run out the force. Just run out the numbers, and so the force exerted by the water on the bend of the pipe is a negative, meaning it's in one direction, and then the reaction of the force exerted by the pipe on the water is the same magnitude but in the opposite direction, that removes the negative sign, and that number happens to be 44.2 kilonewtons. And so that gave us a chance to apply the impulse momentum equation to compute the force exerted by water in a bend on a pipe, or same thing on any type of an object or any wall to a container, anything that diverts the flow, changes the direction of the flow, changes in momentum. Okay, conservation of mass, conservation of momentum. That leaves us the third and the last conservation concept is conservation of energy, and this is a real workhorse in fluid mechanics that we'll solve a lot of problems with. And as we solve problems, often we'll combine conservation of energy with conservation of mass. And so the basic concept of energy is that, and in engineering applications, we like to talk in terms of head. And so we went to the basic derivation of the Euler equation. We would derive energy per unit mass, and then we'd divide by G, and we'd get energy per unit weight. And so that's convenient to work with, because if you've got energy and say Newton meters per unit weight, Newton meters per Newton, that gives you head in meters, which is quite convenient. Or in the English system, energy in foot-pounds, and then if you've got a unit energy per unit weight, you've got foot-pounds of energy per pound of flowing fluid, and that gives you feet. And so the actual head comes out in units of meters or feet, and that's why that's quite convenient in applications. That's why we talk in terms of energy head. And so the total energy head is the elevation head, which is a potential energy. If you visualize a particle of flowing fluid, it has the potential under the force of gravity to drop through some distance z, and so that's we call it elevation head. And then there'll be a pressure exerted on that element of the fluid, and the pressure head is the pressure divided by the unit weight of the fluid, and it goes back to the equation that we worked with in fluid statics, same concept as fluid statics. And then a velocity head, there's kinetic energy, and the velocity head is v squared over 2g. And so that's the total head. And if we write Bernoulli's equation for an ideal fluid without frictional resistance or head losses, we're just saying the elevation head at one location plus the pressure head, same location, plus the velocity head at that location are equal to the summation of the same terms at another location, in a channel, in a pipe, or whatever. But in reality, in a non-ideal fluid, you have frictional resistance and head losses. As the hydraulic energy is converted to heat energy and dissipated to the environment, and so we have a head loss term. So we've got the total energy upstream is equal to the total energy downstream plus the head loss that occurs between the 2 points. That's the basic equation that has an absolute multitude of different types of applications. And we could begin any place with the applications, and this particular example gives us opportunity to look at a measuring device and at the same time apply the basic energy equation. And the measuring device is called a pitot tube, and what it measures is a point velocity. So if you have a flowing fluid, and of course the velocity, there'll be a velocity distribution. If it's in a pipe, in a pressure conduit, or open channel, or whatever, the velocity will vary. And this is an instrument to measure the velocity at that point. And so what we want to measure is the velocity right there in the fluid. And so what we're going to actually measure is how high the water rises in the pitot tube. And we'll use that measurement to then compute the velocity there. And so this is just a tube, and just a simple tube that's open it's open on this end, but it's also open on this end. And so what happens is the fluid, the liquid, flows up into the tube, and we know the velocity right there. There is no velocity. It's stagnant. So in the tube, there's zero velocity. But outside of the tube, there's the velocity, that point velocity we're trying to measure. And so what we're really going to do is we're going to have a conversion of energy from a velocity head to a static pressure here. And so we can formally do that by just looking at the energy equation. This gives us an opportunity to apply the energy equation, and so we apply it between a couple points. We'll apply it between a point right here and a point right outside. Right in the entrance to the tube and just outside the entrance to the tube. And so if we let point 1 be right inside the entrance to the tube, and we can put the datum any place we want to put it. Let's just put the datum right here. And so that'll be our arbitrarily selected horizontal datum. And so it's right through the center line of the entrance to the tube, and so Z1 is going to come out to be 0. Now, the pressure head is whatever pressure head is in there. We don't know what that is. We're going to call that P naught over gamma. That's the pressure head at the entrance to this pitot tube. And then the velocity is 0. Once the water gets in there, it's not moving anymore. And so there's 0 velocity. Now, if you're outside the entrance to the tube, and say we're at the same vertical elevation, so our Z is still 0, and we've got some pressure, and this is the pressure head. You know, if you're outside the tube, the pressure head from fluid statics, no different than from fluid static, it's just the pressure would be the gamma times the vertical difference in elevation between the water surface down to this point of interest to us, out here in front of the pitot tube, and so that's just the pressure divided by gamma. And so we can call it whatever. We'll call it PS, stagnation pressure. And then there is a velocity. When you get away from the pitot tube, there's some velocity. And so some of the terms went to 0, and this is true of many of your applications of energy equations, that you'll write the energy equation between 2 points for your particular problem and plug in terms, and some of them will go to 0 depending on the application. And these are the ones that don't go to 0. And so we've got the pressure head inside the pitot tube entrance, and then we've got the pressure outside in the flowing water. On one side, and the velocity, and that's equal to the velocity head. Now, and so really, and this is also true of applications in general, what we're really doing is we're trading off between the elevation head's the same. The elevation head's the same, so we're just trading pressure head for velocity head. And so inside and outside, we've lost velocity head as we went inside, and where did we pick it up? We picked it up as an additional head here. That's just additional pressure head that's equivalent to the velocity head that's outside the pitot tube. That's the trade-off. In all of your energy problems, it's an accounting system. Elevation head, pressure head, velocity head. At one location, the same terms at another location. Something happens, you change some dimension of the pressure conduit, and you lose either pressure head, elevation head, or velocity head, and you've got to pick it up someplace else. There's got to be a trade-off. And of course, then very quickly we'll add that other term, head loss, and we'll essentially there's no head loss in this problem. There is no head loss term. And so basically this head, and what that head is, it's the difference in the pressure head inside and outside of the entrance to the pitot tube. And that difference in head is just simply the velocity head. And that's always going to be the case with a pitot tube. So in a pitot tube, you can always measure the head, how much the water rises up from the water surface or the liquid surface up in the tube, and plug it into this equation to get the velocity. And so in this example, and this is an adaptation, a little bit of a variation of an example that's also presented in your EIT review reference book, and we just changed it just a bit. But here we've measured this height, and we measured it to be 7.3 centimeters, and so we want to know the velocity at this point in the flow. And we've already worked the problem. All the problems are the same for pitot tube. You start with energy equation. It's going to come down to this equation from the previous set of page of notes, and so we just plug in our measured 7.3 centimeters here, get the units correct, consistent. We plug it in meters, since we're going to be using meters per square second for the acceleration of gravity, and we get a velocity of 1.2 meters per second. So that example, it's a classic application of the energy equation, but it also illustrates a particular device for measuring velocities in a fluid flow field. This diagram shows all the different terms, or at least many. We're going to actually look at a couple more terms too, because we're going to add a pump, and we're going to add pumping head to it. But assuming we have no pump, this shows the different terms. And hydraulic grade line, there's a whole category of problems in dealing with hydraulic grades. And so the basic definitions are given here schematically. And again, we've drawn this for a pressure conduit, for a pipe. It could be drawn for an open channel, different types of systems. But basically, we've got the energy at one location, which we're relating to the energy at another location. And the energy is the elevation head. And all of these are in terms of vertical heights in meters or feet. And so an elevation head above a datum. And so if we're interested in the, say, this point and this point, a streamline going through these 2 points in the center of this pipe, that point is some elevation above the datum. It has some pressure, and so if you can visualize the pressure, if you drilled a hole in the side of the pipe and inserted a piezometer tube, the water would rise to right there. By definition, that's your hydraulic grade. That's how high water would rise in a tube that was inserted into the pipe. And that's why we call it a pressure conduit, because it's not at atmospheric, you don't have a free water surface at atmospheric pressure. You've got a confined flow situation where there's some pressure other than atmospheric pressure. So that by definition is the hydraulic grade. And of course we got a hydraulic grade at any location. And if you connected the hydraulic grades at all the locations along a pipe or along a pressure conduit system, you get your hydraulic grade line. Now we also have velocity head. The water's flowing. There's a kinetic energy. And so when you add your velocity head, and it's going to be in meters or feet too, it's a head. It's a energy per unit weight of flowing fluid, foot-pounds per pound, or newton meters per newton. And so you add that and you get the energy line. Now, in an ideal fluid, assuming no frictional resistance, that would be a horizontal line. But what happens is, with the turbulence of the flow and with the fluid particles meeting resistance from the walls of the pipe or the conduit, there's energy losses. The hydraulic energy is dissipated as heat to the environment, and so there's the energy line slopes, and we have head losses represented by this distance here. And so we write the energy equation. The energy at one location, the three terms, is equal to the energy at the other location plus the head loss. And this takes us back to fluid statics. The pressure term is really the hydrostatic pressure distribution term from fluid statics. That, remember, pressure is just gamma times H. And we work with this equation earlier in fluid statics. Now we express it as a head. The head is the pressure divided by the gamma. And in many engineering applications, just I guess around your house type applications, just water in a distribution system. If we wanted to do conversions, you can go through the conversions, and in the English system, 1 pound per square inch is equivalent to about 2.31 feet of head. So in a municipal water distribution system, typically we try to keep pressures at about 60 to 80 pounds per square inch, and so that's equivalent to about 135 to 185 feet of head by plugging into your equations. And so faucet pressures at your house, you'd typically like to be above 5 psi, which is about 11.5 feet of pressure. And so you'd like to, at your home, be able to think that you could hook up a garden hose to your faucet outside and hold the garden hose 11.5 feet or more above the ground and still have water flowing out of it, if you meet the criteria that most cities have. And in the water mains, about 80.8 feet of head. So that's just to think intuitively as far as pressures and heads in a pressure conduit system. And many of the problems that you solve is just a trade-off, as we said already, between the different forms of energy, the elevation head, the pressure head, the velocity head. And this illustrates some of the trade-offs, and it also illustrates that we can actually add energy to the fluid in the form of a pump. Head losses remove the energy, but we can also add energy in form of a pump. And so we've expanded the energy equation just a bit. Elevation head plus pressure head plus velocity head at the upstream location, plus any pumps head added between the two locations is equal to elevation head plus pressure head plus velocity head at the downstream location, plus any of the head loss that occurred between the upstream and downstream locations and that length of the pressure conduit. And so what a pump does, a pump just simply raises the energy line in the hydraulic grade line. And so the does nothing to the velocity. You know, intuitively, you might, solving a problem, erroneously think in terms of the pump adds velocity, but it can't add velocity. The discharge is the same. Conservation of mass, flow in is equal to flow out. The only way you're going to change the velocity is to change the diameter of the pressure conduit. And so if you come over here and you change the diameter of the pressure conduit, that's going to change the velocity and thus change the velocity head. If you change the velocity head, there's got to be a change someplace else. This is an accounting system. Whenever you add velocity or head and or subtract velocity head, it's got to come from either pressure head or elevation head. And so we can see in this case we made the diameter of the pipe larger as the water is flowing from left to right, and that decreased the velocity head, and so that came from pressure head. As we decrease the velocity head, we increase the pressure head. And if we were to change an elevation so that we dropped an elevation head, of course that would increase the pressure head as well. So the point is there's a trade-off between the different forms of energy in the energy equation. And then a key term in many applications is the head loss term. We were able, in the P2 tube example earlier, assume there was no head loss. We were picking points adjacent just to the entrance of the pitot tube, but in some pressure conduit of some length, there's going to be head losses. And so we've got to be able to estimate head losses. And that's the direction we're going now, is to look at ways of estimating the head loss term in the energy equation. And one common way of doing that is the Darcy-Weibach equation. And it's well accepted, and it of course has particular significance to us because it's the equation that they chose to include in the reference manual. So the basic equation for estimating head loss here, it's empirical in the sense that there's a friction factor, that comes from empirical data, which that data is also furnished in the reference manual, so we'll be able to estimate the friction factor. So it's a roughness coefficient times the length of the pipe for the pressure conduit divided by the diameter times the velocity hit. And so that's an empirical equation widely used to estimate head losses in a pipe. And so it's dimensionally a correct equation, so you can use either feet or meters, feet per second or meters per second, and either English or metric units work fine. And this friction factor, as we're about to see, will be a function of two terms. One's going to be a Reynolds number, which is a representation of flow characteristics, and the other is going to be a relative roughness, which is a representation of the pipe characteristics. So head losses are a function of both the pipe characteristics and the flow characteristics, and the way we're going to characterize the pipe is there's an epsilon, which is a function of the type of pipe, and then that's the absolute roughness, and then the relative roughness is epsilon over d. And so we want to be able to apply this equation, the Darcy-Weibach equation, so the key term here is to be able to estimate the friction factor F. So we've got to focus our attention on this F here for a moment. And so this I've Xeroxed out of your manual. And this is the Moody diagram that's been around for several decades now. And people did a lot of experiments over many, many years and some of the early experiments you can actually visualize to help you understand the concept of an epsilon. And this is an absolute roughness. So if you picture a pipe, and inside the pipe, and people actually in some of the early experiments actually glued sand grains inside the pipe so they could have a measured amount of roughness, and then they could change the roughness. So that epsilon is a representative average roughness on the inside of the pipe. And of course, the rougher the pipe, the more head loss you would anticipate. And so in your reference manual, you'll find a very brief table, and other references are very extensive tables that for different types of pipe give you the roughnesses in either meters or in feet. And so those are, now if you've got a rough pipe, but it's a big pipe with a large diameter, it's going to have a different effect on the flow if it's the same pipe material, the same amount of roughness represented by the epsilon, but a smaller diameter. So what's going to really count is the relative roughness, which is the absolute roughness of the roughnesses on the inside of the pipe divided by the diameter. And so on this scale of the Moody diagram, we've got the absolute roughness divided by the diameter of the pipe. Friction factor is going to depend upon the characteristic of the pipe. Now it also depends upon the characteristic of the flow. And so we use Reynolds number. And Reynolds number is one of those dimensionless numbers. It's the velocity times the diameter times the kinematic viscosity. And it's actually a representation of an inertia forces to the frictional resistance forces in the pipe. And so that's across this scale. And then the friction factor for use in the Darcy-Weibach equation is what we're reading from the scale. And there's different areas of the Moody diagram. And so another concept in fluid mechanics, which comes into play here, which we mentioned very briefly in another application, is the concept of laminar versus turbulent flow. And again, laminar flow is where you've got smooth layers of flow, just smoothly flowing one layer over the other. Turbulent flow is random motions, as the fluid particles are going this way and that way in a random fluid flow field. And so if you have laminar flow, and we use the Reynolds number to differentiate between laminar and turbulent flow. And so if you have a small Reynolds number, and down in this area, we've got a linear relationship here between Reynolds number and friction factor. And in most engineering applications, we'll have turbulent flow, so we'll be out here. And there's a certain area which we call a smooth pipe flow. And this is the bottom line here. And so, by definition, a smooth pipe is a pipe that if you look at the roughness, this epsilon, the little height of the roughnesses inside the pipe, those roughnesses are small enough so that the laminar boundary layer, even if you have turbulent flow in the pressure conduit, at the boundary layer, or at the contact between the liquid and the boundary, there will be a laminar boundary layer. Now that laminar boundary layer completely covers up the roughnesses. Then the flow turbulence never sees those roughnesses. And we call that smooth pipe. And that's represented by this line. And you'll notice that no one bothers to put any lines below that. And so what do you do if you get a point right here? Well, what you do, you just go up for that particular Reynolds number. It's a smooth pipe, and so it doesn't matter that the roughnesses are even smoother. And so you just go up and you read this point. You don't read across there. You go up and read off that curve, off the smooth pipe curve. Now, as you go in this area, if you pick any line, you'll notice there's a curve like this. There's a curvature to it. Because in this region, the friction factor is a function of both flow characteristics represented by the Reynolds number and pipe characteristics represented by relative roughness. But if the flow gets, the velocities get high enough, high velocity means high Reynolds number, these lines get horizontal, meaning that the friction factor, the frictional head loss roughness coefficient term is no longer dependent upon Reynolds number. It's constant with Reynolds number, and then it's just dependent upon changes in pipe roughness far enough out. We call that the fully rough zone. Okay, so the different concepts of flow head losses are reflected in this diagram, and also it provides a mechanism so that when you've got problems to solve and you need the friction factor, you can just come and read the friction factors off the diagram. And the diagram is included in the reference manual, so it's readily available to you for the exam. Okay, so let's use the Darcy-Weibach equation with the Moody diagram to estimate a value for the friction factor. And so we've got a discharge of 1 cubic foot per second flowing in a pipe, and we want to compute the head loss in 1,500 feet of new 6-inch diameter pipe. And in this problem, it gives us epsilon at 0.00085 feet, representative roughness there. And we're going to assume a water temperature of 60 degrees Fahrenheit, and what that's going to do for us is going to give us a kinematic viscosity. And so at 60 degrees Fahrenheit, the kinematic viscosity is 1.217 times 10 to the minus 5th feet squared per second. And we've got a circular pipe, and area is 1/4 pi d squared, so we got the area of the pipe. Here's an equation that we've seen several times already. Velocity is just the volumetric flow rate divided by the cross-sectional area for which the flow is flowing. So V's Q over A, and we can get a mean velocity. We'll need that mean velocity to compute the Reynolds number. And so kinematic viscosity, mean velocity, diameter of the pipe is given. That's all we need to know to get the Reynolds number. And so we plug in the velocity, diameter of the pipe, kinematic viscosity, which is, remember, absolute viscosity divided by density, and we get a Reynolds number of 2.09 times 10 to the 5th. The pipe is characterized by roughness, and we divide that by the diameter of the pipe to get a relative roughness of 0.0017, and these are the two numbers that we need, and the only reason for getting these two numbers is to be able to then get the friction factor from the Moody diagram. And so we go back to our Moody diagram, and we've got a Reynolds number on the horizontal bottom scale here. Ours is times 10 to the 6th, so it's going to be over here, and it's 2.09, so it's going to be right in here someplace. And then we've got a relative roughness of .0017, 2 zeros. So there's a .001 and there's a .002, so it's got to be in there someplace. And so you've got to sort of eyeball, do a little interpolation. I'm looking for .0017, so it's got to be between those two someplace, so it's going to be in there like so. I've got the Reynolds number, and it's going to project up, so we're right in there someplace. And so having found that point, we read across to right over here, and we get a friction factor of .023. So the Moody diagram served its purpose. It gave us the friction factor that we needed to plug into the Darcy-Weibach equation. And so there's the number we read. We put it in Darcy-Weibach equation here. The length of the pipe is given as 1,500 feet. The diameter of the pipe is given as a half a foot. And then the velocity head term, we need the velocity, which actually we computed the velocity up here to get the Reynolds number, and we can use it here in the velocity head as well, divided by 2 times acceleration of gravity. And so that gives us 27.8 feet of head and 1,500 feet of pipe. Now the Darcy-Weibach equation estimates head loss in a straight section of pipe only. And so there's a lot of other components of a pressure conduit system. You have bends, you've got expansions, contractions, fittings, valves, different other types of fittings. And so we have to add the additional head loss anytime anything causes turbulence. Any roughness, any change in direction, anything that causes turbulence causes additional head loss. Additional head loss over and above the Darcy-Weibach frictional head loss in just a straight section of pressure conduit. And so a common term for these other head losses are minor losses. And in many applications, the minor losses might be quite major, but that's what we call them. And so, and they can be expressed in different formats. Your reference manual, the formats are always in the general form of head loss is some minor loss coefficient times a velocity head. And your reference manual uses the term C for the minor loss coefficient. In the literature, there are volumes that give minor loss coefficients for different types of valves, different types of fittings, and so forth. Now, your reference manual that you take into the exam that you're using for gives this table. And so you've got just a few values for a few cases. And so, and we can look at different entrance losses. Well, actually, we just got a couple cases of exit losses and a few cases of entrance losses for which we've got the data given in this table, which is Xerox from the manual. Okay, we'll use these values in this next example. And so this example is a classic fluid mechanics problem of connecting 2 storage tanks with a pipe. And it'll give us an opportunity to use the energy equation. And as we use the energy equation, we got a head loss term. And so we can use the Darcy-Weibach equation to get the frictional head losses. But we also have an entrance because the water goes from the reservoir, from the storage tank into the pipe. So there's an additional head loss there. Plus, the water goes from the pipe into this container, and there's an additional head loss there. So that'll give us a chance to include in this head loss term, include the minor losses as well as the frictional losses, in which Darcy-Weibach tells us how much head loss occurs along the pipe. And so we can apply the energy equation. Another application of the energy equation. It's certainly a workhorse in fluid mechanics. And so all the energy equation applications, we've got to use a little bit of ingenuity to pick out a couple points that have significance. And the significance is usually because we know certain values at those points. And so we'll call this point 1, and we'll call this point 2. And we can define the datum wherever we like, unless for convenience say this is the horizontal datum, the water surface at the downstream reservoir. And so we write the energy equation between those 2 points. And we've seen it several times already in this session, and here it is reproduced again. And so At this point, at point 1, the elevation head, well, the problem statement says it's 30 feet above the water surface here, so we've got Z1 of 30 feet. Now, what about the pressure head? Well, the reason I didn't just arbitrarily pick a point, I picked it in the water surface on purpose because I know the pressure there. It's 0. Because I choose to use gauge pressure, and that means atmospheric pressure is 0. And so that takes care of that term for me. Now, we make an assumption that's very common and would be quite allowable, and that is when you've got a storage tank, even though water's flowing out, there's going to be some flow. We assume 0 velocity here. And so the velocity head there will be 0. And when we come here, now the reference datum takes us right through the water surface. We set that up for convenience, and so we got an elevation head of 0. And the pressure head is 0 too. That's atmospheric pressure again. There's no velocity head again. And so what have we just figured out? That the head loss is the difference in water surface elevation between those two storage reservoirs. And that will always be the case. And the classic problem that crops up quite frequently of connecting two containers of a liquid with a pipe, the head loss is going to always be the difference in the surface of the liquid in the two containers. And the energy equation does that for you and shows you that that's the case. Okay, so if the head loss is equal to 30 feet, what we've got to do is write a head loss expression, and because what we're actually trying to compute is the flow rate. And we'll do that. And we'll recognize that the head losses are in two forms. The pipe friction, which is represented by the Darcy-Weibach equation, and then the minor losses, which in this problem is just an entrance and an exit, which is fortunate because our table just has entrances and exits. It doesn't have anything for valves and other fittings. And so the relative roughness, we can go to the table associated with the Moody diagram and get a relative roughness or an absolute roughness of 0.0015 feet. The diameter of the pipe is 0.5 feet, and so the epsilon divided by the diameter is 0.003. And we've got a problem. And the problem is that to go to the Moody diagram, we need to be able to know the Reynolds number. But the Reynolds number requires a velocity, and we don't know the velocity. As a matter of fact, we're trying to compute the discharge. Once we know the discharge, we'll know the velocity, but we don't know the discharge. We're trying to compute it. And that's not a major problem, certainly an inconvenience for me. But at least I know the relative roughness of 0.003. Let's see, 0.003. It must be between these two numbers. No, it's 3 zeros, so it's right in between these numbers. And so we're right in there. And so if the Reynolds number is high enough, we know what the friction factor is. As the Reynolds number gets lower, it starts curving. And so we're not sure what the friction factor is without knowing the Reynolds number. But what we can do is say, in this range, we can make a pretty good guess, and I'm going to guess 0.016. And then I can come back and check that. So, having used a bit of judgment with our Moody diagram, I assume 0.01, that's not arbitrary now, you know, pretty good guess of 0.016. I'm saying I'm assumed it. And I can easily come back and check it because once the problem's solved, I know the discharge and I can compute the Reynolds number and see if I'm in the right range or not. And if I'm not in the right range, I'll just go through the computations again. And so we plug in the number for the friction factor and the length of the pipe, the diameter of the pipe. We don't know the velocity head, as we just said, and so we just write down the velocity head, and we find that the head loss in that 500-foot long length of pipe is 16 times the velocity head. But we also have entrance and exit losses, and so we go back to a table, Xerox from the manual, and in this problem we got a sharp exit and a sharp exit, sharp entrance and exit. And so we're going to use a 0.5, and that's a pretty standard number for a sharp-edged entrance, and a 1.0 for the exit. Basically, what this is saying, when you exit, whatever velocity you've got in the pipe, you're losing all of it as it dissipates into the static pool of water in the reservoir. And so the entrance loss is 0.5 times velocity head, the exit loss is 1 times velocity head, and so the minor losses are 1.5 times velocity head. And so we can add the frictional losses in the pipe to the minor losses, and we get that the total head loss is 17.5 times velocity head. And at the very beginning, we did an exercise in which we applied the energy equation and found out that the total head loss between those points is 30 feet, which is the vertical distance and difference in elevation between the water surfaces. And so we can set our 16 plus 1.5, our 17.5 times velocity head equal to 30 feet. And when we do that, we get a velocity of 10.5 feet per second. Of course, recognizing that the acceleration of gravity is 32.2 feet per second and plugging in for the G as well. I did have to make this assumption. So we're worried a bit about this assumption. We can check it now just to feel certain that we're okay in that regard. And so having just computed the velocity, I can compute the Reynolds number. And so we say Reynolds number is velocity times the diameter of the pipe divided by the kinematic viscosity of the fluid. And we get a Reynolds number of 4.3 times 10 to the fifth. And we're hoping it's a big number, so it's far enough out so that the initial assumption is correct. And well, we got 4.3 times 10 to the fifth. 10 to the fifth is, there's a 10 to the fifth, and a 4 is right in there, and so it puts us right up here, right in here. And when I read it off very precisely, I read off something like 0.0164. And so I'll say close enough. And so we'll go ahead and accept that. That's a judgment call. Now, if this wasn't the same number, I made an initial estimate of 0.016, and so that came out to 0.018 or something else. Then what I would have to do to actually have the correct answer is I'd have to come back to the original problem, and whatever number I read off, I'd have to plug that number in, recompute that number, and then having recomputed that number, we could combine the friction losses with the minor losses and get a different number here, which would give us a little different velocity, and recheck it again. So that confirmed that the friction factor is close enough, and we just computed the velocity. We were asked for the volumetric flow rate, the discharge rate. So we multiply the velocity times the area. We'll get a discharge rate of 2.06 cubic feet per second, flowing from one container to the other. Okay, we enjoyed the problem so much, we're going to do it all over again. And the only thing we're going to do differently is we want the water to go the opposite way. Now, water normally runs downhill, and so to get the water to go from a storage facility that has a lower water surface up to a higher storage facility, we're going to have to put in a pump. And so we want to assume a pump is added to this example, and we're going to make the water flow the opposite way now with the pump. And what pump head is required for a discharge of 2 cubic feet per second. So that gives us a chance to expand our energy equation to include that pump head term in the energy equation. And so a lot of the problem is the same as before. We got the area, same area as before. This time the discharge rate is given, and since the discharge rate is given, we can divide that by the area of the pipe, velocity Q divided by A, to get the mean flow velocity in the pipe. And we could go ahead and plug into the Darcy-Weibach equation, but remember when we plugged into the Darcy-Weibach equation in the previous example, we got the head loss of 17.5 times velocity head. We'd get the same answer again, nothing's changed. And this time, though, we know the velocity, so we can go ahead and plug the velocity in. We're given the discharge in this problem. And so given the discharge, we can plug it into this expression and get a head loss of 28.2 feet. And now we want to, we know the head loss term, and we want to compute the pump head term. And so here's the energy equation again, the same old energy equation that we've used starting with the pitot tube and continuing to use again. And in the previous example, the head loss got significant. We included the head loss term. Now we've got the complete equation. We've got the pump head term as well, which is going to be non-zero. And so we plug in what we know. And so again, we look at the water surfaces, write 0.1, and actually we're going to reverse this just a bit. Last time, when we picked the 2 points, we went 1 and 2. This time, let this be 0.1. And let this be 0.2. We're flowing in the opposite direction. And again, pressure head is 0, pressure head is 0, velocity head 0, velocity head 0. And we define the datum so that Z1 is 0, and Z2, the water surface at number 2 point, is 30 feet. And so when we plug everything in, we've got everything except the pump head. And so the pump head is 30 plus 28.2. So that sort of tells us what we intuitively know. You know, you ask the question, what does the pump have to do? Well, the pump has to lift the water 30 feet. Since one water surface is 30 feet higher than the other, the pump's got to lift the water 30 feet. But what else does it have to do? It has to overcome the head loss. So the pump takes care of the 30 feet of delta Z lift plus a 28.2 feet of head loss to provide 58.2 feet of head. And the energy equation lets us formally do what we can intuitively figure out would need to be the case anyway. And while we're talking about pumps, we can talk about power and energy and how that fits into fluid mechanics. And remember now, energy is just the ability to do work, and work is force through a distance, and power is the rate of transferring energy, or it's a work per unit of time. And so power is actually it's energy per time. And so if you got energy per time, if you take a weight per time and multiply that by an energy per weight, that gives you an energy per time. And so in energy per weight, that's head. That's what we've been working with all of the time. And you know, H for head. And then as far as a weight per time, if you've got a volume per time, a volume per time, a Q, and you multiply that by weight per volume, that gives you a weight per time. And so we've got a volume per time, a Q, a volumetric flow rate. You multiply that by unit weight, and that gives you a weight per time. And then you multiply that by head, and a head is an energy per weight, and that gives you power. And so that's our power equation. And in the metric system, we use the kilowatt, and so energy would be a kilonewton times meter, but this is a rate, so it's kilonewton times meter per second, and that's termed a kilowatt. In the English system, we use the horsepower, and a horsepower is 550 foot-pounds per second. And so the conversion between English and metric is 1 horsepower is 0.746 kilowatts. So there's the power equation. I did leave out a term earlier in that we just wrote the power equation, but actually when we're talking about pumps or turbines, hydraulic machinery that we deal with in fluid mechanics, in which we're converting between electrical and hydraulic energy, there's never a perfect conversion. There's always an efficiency involved. And I've written the power equation here in terms of pumps now. And so the efficiency is just a number less than 1. That's the ratio of the hydraulic energy supplied by divided by the electrical, or the hydraulic energy produced divided by the electrical energy supplied. And so we'll divide by the efficiency. If it's a turbine electrical generation problem where you're converting the flow of water to electrical power, we'd be multiplying by the efficiency. And so again, the basic power equation, we've got power in kilowatts, kilonewton meters per second. We've got the unit weight of the fluid going through the pump in kilonewtons per cubic meter, and we've got the discharge rate of water going through the pump in cubic meters per second. We've got the head, the difference in energy head upstream and downstream of the pump in meters, and then we've got an efficiency relating electrical to hydraulic power. In the English system, we add a little oddity in that people like the term horsepower or brake horsepower, and so same equation except you plug in a 550, and the 550 is a conversion factor. It's 550 foot-pounds per second is equal to a horsepower. So if we wanted to determine the horsepower required for the pump of the previous problem, assuming the pump efficiency is 75%, and in the example we just finished, we were given a discharge rate of 2 cubic feet per second, and we computed the pump head required to pump that discharge rate, and we got 58.2 feet. This problem is telling us that the efficiency is 0.75, and this is giving us some numbers to plug into the power equation. And so in the metric units, the only difference, there'd be no 550. And so we plug in the numbers, the unit weight of the water, the flow rate, the discharge rate, the head, the efficiency, and we figure out that we need 17.6 horsepower. So we need a 17.6 horsepower pump to achieve what we set out to achieve in that previous example problem. Please, if you would, please, you can now change to the second tape.